responsibilities for its appropriate use. Your failure to comply with these rules could, in some circumstances, be a reason for your discontinuation from this network. And as I said, there was an unfortunate circumstance when it had to be referred to UTM-DIN in the summer of 2021. So I'm professional on reinforcing the rules. When it's needed, I act promptly and appropriately. Is this clear? And some comments, actually, which I reviewed, and some responses were quite appropriate. And I'm actually going to comment on some questions discussed. So probably remove this. So let me first say on what is to be discussed today. Yes, so it will be continuation of the discussion. Of some concepts from lecture 3. Then consideration of some relevant examples. And also some new concepts. A few things were deferred from the third lecture. So I slowed down, as I hope you all realized. Now, there was some confusion about the use of notation. So that's what we used for the power set. So we use 2 to s or 2 to omega. This is not number 2 raised to the power, which is asset. It is not to be recognized like that. Yeah, some thought when you see number 2, so you think it's like 2 in a certain power. No, it is not. And but there is some rationale behind this notation. However, there is some rationale in the use of such notation. And this was already addressed in the example considered at the end of Wednesday's class meeting. in particular assert that if your sample space is finite, in our case it was 2 with a toss of a coin, yeah, so 2 raised to the power 2, which is the number of sample points in our finite sample space, gave us the total number of events in the sigma algebra to be considered. Do you all remember this? And it's one of the reasons why such notation 2s is used. In particular, so what we often get is that the cardinality of the set of all the subsets in the case of a finite sample space equals 2 raised to the power equal to the cardinality of the sample space. Understood? And I think Mike Chen's response, given along the same lines, was quite appropriate. Okay? So I'm thankful for that, Mike. Okay, and I want to continue talking about sigma fields for some time. Like I'll discuss some abstract things first. How many sigma fields do we have? How are they structured? What about building up the probability structure on them? So that is what is to be discussed next. So please, this is all recorded. Yes, so I'm going to erase it now. Now, I consider script F1, which is comprised of just 2 events, the whole sample space capital S and empty space or empty set omega. Not omega, slashed O. So S and the impossible event. Is this collection of 2 events a sigma field or not? Yes. That's what is called the trivial sigma field. Okay. Now consider script F2, which is the power set 2s. Is it a sigma field or not? Yes. Therefore, we produced two different sigma fields. There is more than one, there could be more than two. What about these two sigma fields? Which one is bigger? The answer is obvious. Of course, the power set, yeah? So clearly, script F1 belongs to script F2. And I hope you guessed why I left so much space here. Because there are some others to be squeezed in. So, and it's not unreasonable to assume. So this is the smallest sigma field, which is trivial, and this is the largest sigma field. But we don't really like extremes. Like extremes are okay. But one is too small, the other one is too big, and as you hopefully remember, there could be some problems. Yes?
The largest in terms of cardinality?
Cardinality could be like continuum, but it would just contain. So you cannot beat it.
Okay.
You cannot beat it.
Okay.
Okay? It just contains all possible subsets. Some of them might not even be events for which we want to define probabilities. Okay? Sometimes it is simply not possible. Is my comment clear? Okay. So, but we are actually hoping for something in between. We want to find a reasonably large sigma field in between. And for this intermediate sigma field, we want to construct the probability measure somehow. Yeah? So we want to find a reasonable, meaningful probability measure. Is this clear? I hope it answers some questions being asked during my Friday office hours, and there were reasonable questions discussed. Yeah? Also, questions along these lines were asked by email and also posted on Course Piazza. Okay? So we don't want extremes, we want something in the middle, or in between really, okay? Now, I hope you remember that if we consider continuous uniform 0-1 distribution, which I hope you remember from C62, well, not from C, but we discussed it in C62, but uniform 0-1 was discussed in B52. So for this distribution on 0-1, on the unit interval, the probability measure for a certain interval from 0-1 is just the length of the interval. Yeah? However, if you are going to use your power set constructed starting from the unit interval, you will not be able to have such a uniform probability measure on interval 0, 1, complying with all three Kolmogorov axioms. I didn't prove it, but I mentioned this property on numerous occasions. Okay? Therefore, you need something smaller than the power set of the unit interval, and of course, this should be bigger than the trivial sigma field. Okay? We will start constructing it this week. So we will discuss Borel sigma field, then Lebesgue measure, and so on. But I certainly want to talk about reasonably simple examples first in order to help you build your intuition. Okay? So okay. So do you remember our last week example considered at the end of Wednesday lecture? So there was just one single toss of a fair die, yeah? Now let's move one step at a time. So in our first example, consider two subsequent tosses of a fair coin, yeah? Okay, and we of course need to define our probability triple, namely the sample space S, script F for our sigma field, and our probability measure. These things in general are not defined uniquely. Okay? But in order to solve a problem, so we ought to choose these three parts of our triple quite smart. Yes, so they all should come together very well. Understood? So therefore, let's start from the sample space. So clearly you can have both being heads or head-tail, and the first can be tail, the other can be head, or two tails, yeah? So HT is not the same as TH. So our sigma field is to be comprised of how many outcomes? 16. Yeah, he's right, 16. So 2S has the cardinality equal to 16, which is 2 to 4, which is 2 raised to the power the cardinality of S. As simple as that. Okay? And these are our sample points. So this example is pretty straightforward, I hope. Yeah? So our sample space is finite, hence the cardinality of our power set should be equal to raised to the power of the cardinality of S. Okay? Now let's list all our events and then assign probabilities to these events, okay? So you learned some quite general concepts, and I want to convince you that they all make sense, okay? We just work out all these details by considering familiar examples. And as I said before, math can be boring. That's life, yeah? So, but we have no choice but to list all these 16 events of our power set, which is our sigma field here. So we are not going to get into measurability problems here for a finite sample space. Okay. So, of course, we need to take into account impossible event, the whole sample space, all 4 elementary outcomes, this is clearly here, yeah? What else should we include? All pairs of elementary outcomes, yeah? HH, HT, HH, TH, HH, TT, HTTH, HTTT, THTT. So, and we have 1, 2, 3. No, 1, 2, 3, 4, 5, 6 pairs. Yeah? So, we need to choose 2 out of 4, yeah? Which is 6, yeah? 4 choose 2 is 6. That's how many different pairs we need to have, yeah? And then we have unions of 3 elementary outcomes, yeah? So we need to continue. So we get HH, HT, TH, HH, HT, TH, HH, TH, TT, and finally HT, TH, TT. Anything else? How many did I write down? 16, yeah, and it's clear. Wait a sec, yeah, I should say that you have triples, and there should be 4 different triples, yeah? Because choosing 3 is the same as crossing 1 that we don't take. Yes?
Sorry, for one of your sets, on the right it says HH, TH.
HH? Oh, yeah. HH, TH. So it's a slip of the chalk. So no, it should be HH, HT, TH, HH. Now I have HH, HT, TH, HH. HTTT, I think, yeah. HT, TT, HH, TT, HT, TH, TT. Did I get it right? Uh-huh. Yeah, go ahead.
Professor, I wonder whether the element, the elementary should be written in the form of sets.
No, we can do it in terms of set, but here it's okay to do it like that. With 16, it's not that bad, but I'll talk about rolling a die. So where it's going to be a longer power set, which I'm not going to be writing. I hope I got it right. And if you do problems of this character, and I'm sure you will, I'm going to keep you busy with this stuff, because that is how you need to learn how to operate with sigma fields, probabilities, etc. Okay? So you'll need to do the things from scratch. I'll make sure you all know this. Okay. But what is our next step? We ought to define probabilities for all these 16 events. Sounds even more exciting or more boring, whatever you like. Yeah? But we have this assumption that tosses are independent of each other, and our coin is fair, chances are 50-50. Hence, it's not such a big deal to assign probabilities to all these 16 events. But that's what we need to do. Okay. So the first two are easy, yeah? P of empty set is 0, P of S is 1, and then probabilities of all 4 elementary outcomes are equal 1/4 each. So P of HH is P of TT, which is P of HT. It's the same as P of TH, and they're all 1/4, yeah? Then, for the unions of 2 elementary outcomes, we get 1/2, of course, yeah? We get it from the assumption of our tossers to be ID Bernoulli trials, or simply Bernoulli trials, because it assumes that they're independent and identically distributed, realizing in one of 2 possibilities. Yeah? So therefore, probability of HH, HT is the same as probability of HH, TH. It's the same as probability of HH, TT. The same as probability of HT, TH. And they're all, so we need to have 6 of them. So here I have 4. So it's the same as probability of HT, TT, and probability of TH, TT, and all these all these 6 probabilities are equal to 1/2 each. And finally, we have 4 unions of 3 elementary outcomes. Now let me write them down. So it will be HH, HT, TH, HH, HT, TT, HH, TH, TT, HT, TH, TT. So, and all these four probabilities should be equal to 3/4 each. So it's not that hard. So it's not a rocket science. So it's a very straightforward example that should help you connect B52 with C62 stuff. Okay? And that is what you will be required to do in more challenging problems of this character, where you deal with a finite sample space. You need to describe your sigma field or sigma algebra, and you need to assign probabilities that are going to comply with all three Kolmogorov axioms. Okay? And it will be up to you to check that all these three axioms are going to be fulfilled for your model. Okay? If at least one of them is not, then you're in trouble. Clear? So I hope you like this example. And clearly, for this example, probability of each event from this set of 16 events equals the number of simple events comprising your event, say A, divided by 4. Is this clear? Because this is an example of the discrete uniform probability model. Okay? So probability for such a model is always the number of elementary outcomes in your composite or even simple event divided by the total number of elementary outcomes in your sample space. Okay? So it's also a review of B52 stuff. So now I want to move on and start talking about random variables. Again, it's something that you learned in B52, but in a reasonably elementary for some students, I understand, still need to review C62 stuff. No, I'm sorry. Some of you actually, C62 stuff is more challenging, but a lot in C62 is just a review of B52 with more challenging math being involved, etc. But say, random variables were considered in B52. Now we are building our muscles, putting new structure, etc. So this could be useful. If you're behind in B52, so it would be useful to watch my Start to 56 videos from UTM. And I also encouraged the Center for Teaching and Learning to hire C62TA for him to work for us, for CMS department, and also for the Center for Teaching and Learning. But it's not up to me. I just make suggestions and issue recommendations, okay? And it's one such example that it's useful to build connections between B52 and C62. Yes? So, I don't know, but I suggested the same TA who is your TA for C62. I suggested for him to work in the Center for Teaching and Learning, but it would be a separate contract and I am not involved. Even CMS department is not involved. But they asked for advice, so I gave them an advice, Mike. Okay. So a random variable, or RV, capital X, is a function from S to R1, or its subset, say the set of all non-negative integers. And then random variables will have particular probability distributions, which we will discuss later on. For B52 purposes, a random variable was just such a function. Okay? And of course, there was a discussion on Piazza, etc. Some were confused if it's a one-to-one function or not. No, it is not a one-to-one function. Some random variables could be one-to-one function, but it's going to be a rarer thing to happen. Okay? There could be more than one elementary outcome for which the value of the random variable is going to be the same number. Say, in the previous example, we could consider a random variable equal to the number of heads observed in two tosses. Like, we don't have to assume that it's a 50-50 model. Yeah? So, and it's just a random variable, which is a function from our sample space to R1 or to a subset of R1. So, for instance, we could consider a random variable equal to the number of heads in two tosses of a coin. And we don't need yet to make assumptions about the probability measure at this stage. So, such a random variable attains the same value equal to 1 at two different sample points, ht and th. Clear? Hence, it does not have to be one-to-one mapping. Clear? But it might, of course. Okay, but that's what you actually saw in B52. It's just a review. That's why I'm saying you might want to watch my UTM videos where this stuff is reviewed to make it easier for you. Okay? But we need to move to C62. And we are going to impose some subtle measurability assumptions. We will have to deal with particular sigma fields and assume some properties for such structures, which are going to be reasonably natural. So we are going to talk about Borel sigma field on R1 as well as on the unit interval. But not today, though. So definitely this coming Wednesday. Understood? So, but it's going to be a very substantial step forward. Namely, we will be dealing with sigma fields and the corresponding measurability properties. Okay? For now, I just want to review what is going to happen when we will move on. Okay? So now, I want to erase it. And so I hope you're all comfortable with this B52 definition with some comments on what we are going to do to make it more exciting. Now I consider what we get in the previous example. Okay, so when we calculate the number of heads and tosses, x of HH is 2, x of TH is the same as x of HT, and they're both equal to 1, and x of TT is equal to 0. Did I miss anything? Did I or not? No. Yeah, you're right. For each elementary outcome out of 4, I defined our number, which is an integer between 0 and 2. Okay? No, I'm okay. But what actually happens is that every random variable on a probability space which we denote as script f and p So each variable induces a probability measure on the real line which is denoted by capital P sub capital X. Or if you don't like putting random variable as a subscript, you can take it within the parentheses, because it's not number P raised to the random power. It's just a notation. Is it clear? Don't make posts. I'm confused. You just listen to me instead of texting your buddies about how boring probability theory is. They know it already, okay? They don't need to be reminded about it. So it's just notation, okay? So you get probability measure on R1. And this probability measure is induced by a particular random variable, capital X, yeah? So, from this new probability measure on R1, we are going to construct CDF, or cumulative distribution function, for your random variable of interest. So your CDF is basically closely related to your induced probability measure on R1. Did you get this connection? So we actually merge two different things studied in B52. Okay? Tell me about different probability measures for previous example of tossing two coins, or it's actually tossing a coin twice. Like we could consider, of course, tossing two coins simultaneously, but they ought to be distinguishable, yeah? A nickel and a dime. But here we assume chances are 50-50, but we could assume that the chances are, say, 2/3 for head and 1/3 for a tail, yeah? So, and then we would get a different probability measure, and we would get a different induced probability measure on R1. Understood? Okay. So, and let me actually conclude this lecture with an important formula. And we need to observe 1 minute of silence. Okay? That's what university recommended us at the end of 12-to-1 lectures, but I will write in silence. So this minute of Queen Elizabeth commemoration is over. We will finish the lecture now with this formula that I'm going to rewrite again at the beginning of Wednesday's class meeting, and you would need to think about this formula between today and Wednesday lectures. You have 47 hours to think on what this formula actually means. Thank you, and I will see you